right, sections 1.1 and 1.2, finding limits. Okay, consider that you have this function x squared minus 1 over x minus 1. Now, if you try to plug in x equals 1, you'll find that you get 0 over 0. Not only does that not exist, it's actually something called indeterminate because you get 0 over 0. We'll talk more about that in a minute. So, you can't plug in the 1, but if you take this function and you factor the top, you see that, hold on, you see that you can cancel those two factors, and you're left with plain old x plus 1. You can plug a 1 into this. What happens when you plug in the 1? You get a real number, a 2. So that value exists. So what we need to be able to examine this function around or close to the value x equals 1 and see the behavior of the graph or the behavior of the y value as x approaches 1. And you'll see that as x approaches the value 1, f of x approaches the value 2. Even though you can't plug x equals 1 directly into the function, you can see how the y value behaves in the area of x equals 1. As x approaches the value of 1, it gets infinitely close. What happens is the y value gets infinitely close to 2. So what we need is a new tool so that we can examine or analyze the function and the behavior of the y value for all values of x. And in this case, the x equals 1 is not in the domain of the function itself. So we need a new tool, and that tool is called a limit. And this statement right here, the way you read this statement is limit as x approaches 1 of the function equals 2. And that's because we were able to factor and cancel. If you plug the 1 directly in, you're going to get 0 over 0. By the way, pretty soon we're going to use that as a clue to know what to do to find the limits of these functions algebraically as opposed to the two ways that I'm about to show you. So what all of this says is the graph of this function is the same as the graph of x plus 1, which is just this straight line right here. The difference is this has a domain restriction built into it. So you see that it's the same graph, but there's an open hole at x equals 1. Okay? Because the value of 1 is not in the domain of this function. Even though you can simplify it, the domain restriction remains. So you have this open hole at x equals 1. Okay, again, notice that when you plugged x equals 1 into that function, you got 0 over 0. That's not just undefined, it's worse, it's indeterminate. And in that case, I want you to pay very close attention because if you get 0 over 0, you know that x minus the number that you plugged in was a factor. And in this case, it's a factor of the top and a factor of the bottom. Therefore, it can be factored and canceled. Cancel it and see what happens. Once you cancel it, you plug the 1 back in and you see what your answer is. Even though canceling removes the 0 in the denominator, which would make it undefined, and you can't do that, the domain restriction from the original function remains even after the canceling. That's what the open circle was. But we call this a removable discontinuity because we canceled it and then we were able to plug in the x plus 1. So just keep all this stuff in mind. The 0 over 0 is very, very important for you to pay attention to. So let's look at this again. If we factor and cancel, we get x plus 1. That's this line. But because the original function had a domain restriction, we have a hole at x equals 1 right here. So what we want to do is what we call a left-hand limit and a right-hand limit. So notice that if I'm coming at x equals 1, hold the phone. Here's where x equals 1, right? So I'm coming at x equals 1 from the left-hand side. So right now x is smaller than 1, and I'm coming at it this way. Now if the x value is traveling along the x-axis like this, what's happening to the y value? It's approaching y equals 2. You see that? Now the right, oh, by the way, that little minus sign, the limit as x approaches 1 minus a little bit. That's less than 1. You're coming from the left-hand side. For the next one, that little plus, that's the right-hand limit because you're coming at it from the right-hand side. This is x plus a little bit. Whereas this is 0.9999999 whatever. This is 1.000000 something. Okay? So you're coming at the value of 1 from bigger than 1 from the right-hand side, and as you approach the x value right there, look what the graph is doing. It's going to 2. So taking a left-hand limit and taking a right-hand limit, and you see that those values are the same. The left hand equals the right hand, therefore the limit exists, and in this case, the limit equals 2. That's the definition of an existing limit, is that the left hand and the right hand are both pointing to the same value. So in this case, when we start talking about discontinuities, we know in this case that x equals 1 is not in the domain of this function, even though the limit exists and both sides are pointing to y equals 2. There's a hole in your graph that makes it a discontinuity, and they call it a removable discontinuity because we were able to factor and cancel the thing on the bottom that caused it to be division by 0. Okay, let's do another example here. Let's look at 1 over x. Obviously, x equals 0 is not in the domain of this function. So f of 0 does not exist. All right? But what happens to the y value when x approaches 0? How close can you get to 0 from either side? You can get infinitely close. Think about it. There are no two numbers on a number line that touch each other. You can always go in between. So the number, that's why we use a line to represent the real numbers in the first place, is because, yeah, it goes to minus infinity on one end and plus infinity on the other, but you can't find 2 points that touch each other because you can always go an infinite number of times between 2 points. So instead of using a bunch of dots to represent the real numbers, we use a line. It's continuous because it's infinite within itself. Isn't that awesome? Don't you have chill bumps right now? I know, right? Okay, so what happens to the y value when x gets infinitely close to 0 from the left, which would be less than, and from the right, which is greater than? Well, let's look at the graph. This is the graph of 1 over x. You can't plug in an x. You can get infinitely close, but you can't get there. And let's think about it. 1 over something is never equal to nothing. If you've got one pizza, you can't cut that pizza into so many slices that you have no pizza left, right? You can always cut a slice in half and in half and in half, no matter how down to atomic level, you can still cut it in half. So this guy is never 0. We'll talk more about these asymptotes later in chapter 3. But if x equals 1, y equals 1. If x equals minus 1, y equals minus 1, right? 1 over the number. If x is a half, y is 2. If x is a third, y is 3. So you see that closer you get to 0, the smaller the denominator, the larger its reciprocal. So this guy is going to positive infinity if x is a positive number. But notice that if I plug in a negative number, I'm going down to negative infinity. And don't laugh at my graphs. I hear you laughing. I know they're messy. As we say 1 over a value and we get closer and closer and closer to 0, teeny tiny numbers, you flip those teeny tinies over, you get really big. But if x is negative, you're going to negative infinity. So we see as we approach 0 from the right and as we approach 0 from the left, we're going to get a positive infinity and a negative infinity. And I've never seen where those two things equal each other, right? So this limit as x approaches 0 doesn't exist. Not only can you not plug 0 in, the limit doesn't exist because your fingers are pointing in opposite directions as you come at it from both sides. Now another way to examine this is numerically. So here I have taken the coming in from the left. Minus 0.1 is to the left of 0, but it's very close. Minus 0.01 is closer, and minus 0.001 is even closer yet. When I plug those into 1 over, you see how my value of y is growing, and it's going to grow bigger and bigger and bigger, but they're negative. So when I approach from the minus side, I'm going to negative infinity. But when I approach from the plus side, see how these positive values are getting closer and closer to 0. As I keep plugging numbers smaller and smaller in, I'm going to go to positive infinity. But negative infinity doesn't equal positive infinity, so the limit does not exist. Remember, the definition of the limit existing is that the left and the right-hand limits are equal to each other. So, what if you have f of x equals 1 over x squared? A squared is always a positive number, right? So, as x approaches 0, when we come at it from the left-hand side, and these numbers are getting closer and closer to 0, but they're negative, when we flip them over, we're squaring them, and we get great big positive numbers. This left-hand limit is going to positive infinity. When we plug in positive numbers and we square them, and these are getting smaller and we're dividing after we square, we're getting really, 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 really big, but they're positive. These two values are the same. We never really get there. So most of the textbooks that you see will say that, here, let me write this down, hold the phone. Most textbooks that you see will say the limit as x approaches 0 of 1 over x squared does not exist. I'm going to do this in different colors here. Some textbooks will say does not exist because you can't get to infinity. Therefore, the limit doesn't exist. Some textbooks will say it diverges, which means it blows up to infinity, which is true, right? But for us in this class, I like to say something that gives us the most information, and I'm going to say that that thing goes to positive infinity. It never gets there, but you know what? In our first example, x squared minus 1 over x minus 1 as x approached 1. We couldn't plug it in, but the left and right hand limit agreed and they were both 2. So we say that the limit equals 2. You know what? It doesn't ever equal 2, it just approaches 2. And this limit right here approaches positive infinity from both sides. If you draw the graph, this one grows a lot faster than the 1 over x does, but both ends are going to positive infinity. So I will accept any of these three answers. It seems to me that this gives you the most information, but you may find in the back of the book does not exist or diverges. So I'll let you go with that. Okay. What happens is if you take the left-hand limit, it goes to positive infinity, they'll say it diverges. You take the right-hand limit, it goes to positive infinity, they'll say it diverges. But if they ask you for the limit, they'll say it doesn't exist. I say both ends are going to positive infinity, and that tells me what my graph looks like. It gives me information. So that's a little bone I have to pick with most textbooks. It doesn't really matter. Section 1.1, your homework is 21 through 59 odd. These problems are set up where you have a graph to look at. I want you to just look at the graph and look at the question that they're asking. You don't even have to write anything down. You just have to understand what the heck's going on. One side's coming from the left, one side's coming from the right. Am I pointing to the same number from both directions, or are my fingers not touching? That's the thing you got to watch for. All right, and I will do a video for 1.2 very soon.